Welcome to section 6.2. We're dealing with the binomial distribution. And this is in chapter 6 because a binomial distribution, it's still a discrete distribution. So our outcomes or our variable is going to have countably many outcomes. And so to create the binomial probability distribution, we are going to look at a binomial experiment. Binomial means two, and so a binomial experiment is an experiment with two outcomes. And we call those outcomes success or failure. All right, and then whatever is considered a success and whatever is considered a failure is determined by the researcher. All right, so that's the first property of the binomial experiment is we have to have two outcomes. There's actually 4 properties to memorize or put on your note card because I'll ask for you guys to verify if something's a binomial experiment. So the first thing is that our experiment has to be performed a fixed amount of times. Okay, so like 5 coin flips, for instance, or roll the die 7 times. We're not allowed to flip the coin until you get 10 heads, because we could actually end up flipping the coin like 100 times. We don't know. So we have to have a set amount of trials. Each repetition of this experiment, that's what we call a trial. So each repetition is called a trial. And we use little n to notate trials. Unfortunately, it's the same notation as sample space, but we'll be able to tell in the context based on the context of the problem. All right, the next criteria is the trials are independent. So stuff like flipping a coin is independent from whatever we flipped right beforehand. Sampling with replacement would be independent. Drawing like 3 cards is not independent, so that wouldn't be considered a binomial experiment. All right, the next thing is what we were just saying up there at the top. Each trial or each experiment has 2 disjoint outcomes. Success or failure. And again, that's determined by the researcher in the context of the problem. All right, and then finally, the 4th one is that the probability of success, we're going to call it P, and that's notation we're going to be using for the rest of this section, is fixed. So kind of related to independence of our trials. All right, and again, we call it P. Okay, so to summarize everything, we have, for a binomial experiment, we have n independent trials. P is probability of success. Since there's 2 outcomes only, the complement 1 minus p is going to be the probability of failure based on the nature of our binomial experiments. All right, and again, this is still a discrete random variable. So x is going to be, we're going to be counting the amount of successes. And now we have a discrete random variable. Okay, so if we have n trials, right, and we're going to count up the amount of successes in each trial, well, each experiment we could have, for instance, all of them could be failures, so we would have 0 successes, or all of our trials could be a success, so then we would have n. So the value of our binomial random variable is going to be between 0 and n. All right, let's look at some examples of experiments. We're going to determine if they're binomial experiments or not. A player rolls a pair of fair die 10 times. The number of 7s rolled is recorded. All right, so let's break this down to see. All right, so the first thing, do we have a fixed amount of trials? And we do. A player rolls the die 10 times. So if I ask you to verify something's a binomial experiment, this is what you should do it. You have to do it related to the problem. So for number 1, we wouldn't write the number of trials is fixed. We would say that the dice are rolled 10 times, because that's relative to the problem. I don't want you to just copy it off your note card. You have to relate it back to the experiment at hand. All right, so the trials are independent. And it's true, if we have a fair die, each roll is independent of the next roll. So there you go. Number 3, each experiment has 2 disjoint outcomes. So again, we wouldn't write that. We would write success is rolling a 7. Because that's what we're recording. So that's a success, since that's what we're looking for. So the failure is everything else. Failure is not rolling a 7 or rolling something else. And those are disjoint. Either it's 7 or it's not. And then finally, the probability of rolling a 7 would be fixed. And we could actually calculate that using classical probability. So probability of rolling a 7 is fixed. All right, and because it upholds all of these criteria, we can conclude that this is a binomial experiment. All right, and again, if we wanted to know the values of our random variable, of our binomial random variable, when we roll the dice 10 times, think of the extremes. Either every roll of the dice, none of them are 7, or if we're really lucky, which probably isn't going to happen, all 10 of them could come up a 7. So the value of our random variable, it's going to be 0 through 10. And then everything in between, right? Maybe when we roll the die 10 times, 3 of those rolls end up being 7, something like that. All right, let's look at this next one. The largest airplanes had an on-time percentage of 84.7% in November. In order to assess reasons for delay, an official with the FAA randomly selects flights until she finds 10 that were not on time. The number of flights that need to be selected is recorded. So is this a binomial experiment? No, not a binomial experiment. And it's not a binomial experiment because the number of trials aren't fixed. She is going to keep randomly selecting flights until she finds 10. So that's why it's not binomial, because there is not a fixed amount of trials. All right. And then finally, part C, in a class of 30 students, 53% are female. The instructor randomly selects 4 students. The number of females selected is recorded. Is this a binomial experiment? No. And it's right here. The instructor randomly selects 4 students. So this is not a binomial experiment because it's sampling without replacement. So it's not independent trials. All right, and then we could also say that the probability of success is not fixed. We could also say that. You can also say P is not fixed. Both are correct. All right, so let's look at an example that is a binomial experiment. So similar to this example, studies have shown that 79% of a certain airline flies out of LAX on time. We randomly select 3 of these flights out of LAX, and we're going to construct a probability distribution for the random variable x. Okay, so just to go over this quickly, fixed amount of trials, it's 3. Independent because it's random. How about that? Each experiment has 2 disjoint outcomes, on time or not on time, and the probability of success is the same. Okay, so it's a binomial probability experiment, and we're going to start getting information about the binomial random variable x. Okay, and we're going to do it by constructing a probability distribution. Okay, so since we're choosing 3, the values of our random variable are going to be between 0 and 3. Whoops, that's an x. All right, so let's construct our probability distribution. So we'll have our values of our binomial random variable and the corresponding probabilities. Out of 3 flights, 0 can be on time, 1 could be on time, 2 or 3 could be on time. And to get these probabilities, let's pick on the probability that 1 is on time. All right, so we're trying to fill in that number right there. So let's find the probability that x is equal to 1. So x is our random variable. Okay, so if 1 flight is on time, let's break this down. I'll use O for on time, L for late. So out of 3 flights, if 1's on time, it could look like the first one's on time, or it could look like the second one's on time. That one's very funny. Or it can look like the third plane we choose is on time. All right, so we have 3 opportunities. Okay, what do we do with that or? We just learned about that in chapter 5. That is plus. All right. Okay, and then let's look at this first one. This is the probability that the first is on time and the second is late and the third is late. So that's what all of these little sub-probabilities are. All right, I'm not going to write all that out. Okay, and then what's that and keyword? Multiplication. So this is really the following. I'm going to switch colors. This is the probability that it's on time times the probability of being late times the probability of being late. All right, etc., etc. And really these three products I have, they each have the same factors. I'm running out of space. This is a product on the very end with limited space. So for instance, they each have two L's, and then they have one probability of being on time. So it's really 3 times that one product, because each of those products are the same, and it's the same 3 times. Okay, so we know all of these. We have the 3. Probability that they're on time is given as 0.79. That's the success. Probability that they're late is the failure, so that's the opposite. So using the complement. All right, and then we're late twice, so we can just square that. And then we get our probability. So the probability that our binomial random variable is 1 is this. All right, so let's go back up to our table, and we can fill that out. It's 0.104517. Okay, and then we can do that for all of them. We would do it for the 0, for the 2, and for the 3. That's how we're going to construct our probability distribution. All right, a little bit tedious, so let's see if we can generalize to a formula. So we just learned about our combinations in section 5.5. So really this is saying we have 3 choices, and we're looking at the combination that 1 is late. Probability of success is P, and there's 1 success, and the rest are going to be failures. So if there was 3 slots, then the rest are failures. Okay, so there you go. So this is our formula. This is our formula for finding probabilities. So let's come on down here and generalize this so we don't have to start from scratch each time. All right, so binomial probability distribution function, PDF, all right? That will be important for our calculator shortcut. But before we get there, we do it by hand. So the probability that our binomial random variable takes on x, so we have n spots, and we have x amount of successes. Probability of success is P, raise that to the x, and then we have our failures the rest of the time. And there you go. Okay, so let's say we wanted to find, going back to our example, the probability that 2 of those flights are on time. It would be 3, choose 2. Probability of success happens twice. The failure happens once. 3 minus 2 is 1. And then you put that into your calculator, and we get 0.393183. All right, and we can come back up to our table and put that in for x equals 2. So 0.393183. All right, so let's look at a more complicated example. All right, so according to Experian Automotive, 35% of all car-owning households have 3 or more cars. Let's look at this first example. It says in a random sample of 20 car-owning households, What is the probability that exactly 5 have 3 or more cars? All right, so if we are sampling from 20 cars, that's like 20 trials. Right, the probability, and it's a random sample, so how we're sampling the households is independent. Probability of success is going to be the same, and we're going to define success as a household having 3 or more cars. I guess that means failure would be 2 or less cars. Okay, so this is a binomial experiment. So this first one, what is the probability that exactly 5 have 3 or more cars? So we have 20 trials, and we're going to fill 5 slots up with successes. Probability of success is 35%. That happens 5 times. Probability of failure is 0.65, and that happens the rest of the time, so 20 minus 5 is 15. All right, so again, n is 20 for this example. P is 0.35. And then x is 5. Okay, so if we put this into our calculator, you could do it in steps. You could do this first, for instance. But we're going to get 0.1272. We'll go 4 decimals out. Okay, so let's look at this next one. So this says in a random sample of 20 car-owning households, so same situations, what's the probability that less than 4 have 3 or more cars? Okay, so I always write out the probability first. So x less than 4. All right, and then we can rewrite that. Because we have a discrete random variable, it's all countable. So we don't have to write less than 4. We want to do less than or equal to. We want to be including our value because it's discrete. So less than 4 is really less than or equal to 3, right? Because the potential values of x are 1, 0, 1, 2, 3, 4, all the way up to 20. Those are the amount of successes we can have. So we're not going to say less than 4. Less than 4 implies less than or equal to 3. All right, and then notice what this means. This would mean if x is less than or equal to 3, it's the same as saying that x is 0 or x is 1 or x is 2 or x is 3. So that means that's 1, 2, 3, 4 probabilities we'd have to add up. That's what we were doing in part A. We would have to do part A 4 times and then add it up. Okay, we could do it. It would just be a little bit tedious. So we're going to take a break here, and we're going to look at our calculator.